Welcome back, students. In this section, we are going to finish up talking about molecular orbital theory. We're going to talk about how we can computationally generate molecular orbitals and just look at some of these molecular orbitals that have been generated through programs like Gaussian and analyze them for bonding and anti-bonding characteristics and so forth. Because as we've already seen, constructing molecular orbitals for polyatomic molecules is very challenging. So we'll just let the computers do it for us and take the information from what they generate. And after this, we'll move on into doing electronic spectroscopy. So the learning goals for this lecture are to continue, as we've been doing for the past couple of lectures, to compare and contrast our valence bond theory and molecular orbital theory. And we'll also look at more complicated molecular orbitals for polyatomic molecules, and we'll want to see what we can say about them in terms of energy and if they're bonding or anti-bonding or non-bonding MOs. And of course, the more atoms you have in the molecule, the more complicated that gets. At the end, we'll consider aromatic and conjugated molecules and their molecular orbitals. So we haven't considered them yet because we can't really do valence bond theory for these molecules because, of course, they have to be non-localized. So we're pretty comfortable with that idea from organic chemistry, and we'll see it applied here in physical chemistry. So to start, we are going to consider these molecular orbitals for formaldehyde. So now we have a more complicated molecule even than we talked about last time when we talked about water. We have a 4-atom molecule, and we want to, say what we can say about these orbitals. So remember that these molecular orbitals are generated from a program like Gaussian without making any assumptions. So when we see here that the lowest energy orbital, this 1a1 orbital, is the 1s orbital around the oxygen atom, that is not built into the program. That's just the nature of reality, that these core electrons are very localized. They don't really participate, they don't really overlap with anything else, and so they just form their own non-bonding orbitals. So we can see here all of the first kind of set of molecular orbitals for this formaldehyde. As we saw last time, the labels here talk about symmetry. And again, we haven't discussed this symmetry yet. We will in the future. So if you're not familiar with this, keep that in mind. We will go over this. But we have these A1 orbitals, and they all have the same type of symmetry. So they're all A1 orbitals. And we'll talk about why that is later. The numbers are talking about increasing energy. So the 1a1 orbital is lower in energy than the 2a1 orbital is lower in energy than the 3a1 orbital, and so forth. So once we come here to the 1b2 orbital, that's the next highest energy orbital, but it has a different type of symmetry than these a1 orbitals. It has a b2 type of symmetry, and it's the first one of its kind, so it gets a 1b2. That's what this nomenclature comes from. So let's look at these orbitals and kind of extract information from them. One thing that we can see, so these orbitals are listed in terms of lowest energy here, and they go up to the highest energy orbital here, this 2b2 orbital. So how can we talk about the energy of these orbitals? The first thing to note is that these 1a1 and 2a1 orbitals are lowest in energy because these are the core electrons. And of course, the core electrons for oxygen will be lower in energy because oxygen is more electronegative than carbon. But here we have these 1s electrons from oxygen and carbon. Now, as we increase in energy outside of that, we actually start to get into the bonding MOs. And what you'll note is that the energy of the MO correlates with the number of nodes. So here in this 3a1 molecular orbital, there is no nodes. So that makes it the lowest energy orbital in terms of the bonding orbitals. If we go up one to the 4a1, we now have a single node. The 1b2 also has a single node. The next highest energy, the 5a1, now has 2 nodes. And here the 2b2 also has 2 nodes. So you'll note that nodes here aren't strictly increasing. We don't have one orbital with 0, one orbital with 1, one orbital with 2, and so forth. But you'll note that as we increase in energy, we also increase in nodes. Of course, the other thing that's going on is overlap. Having more overlap, having direct overlap from sigma orbitals is better than having indirect overlap from pi orbitals. So that complicates these things, and we can have multiple orbitals, each with one node that have differences in energy due to the different kinds of overlap that they have. Another thing we are likely interested in is which of these orbitals are bonding and which of these orbitals are maybe anti-bonding or non-bonding. And of course, this question becomes more complicated. So you'll remember that our definition essentially of bonding and anti-bonding was, is there electron density between the atoms? If so, it's bonding. Is there a node between the atoms? If so, it's anti-bonding. And if there's neither electron density nor a node, then it's non-bonding. Now here we have 3 bonds. So there's a difference in terms of what molecular orbitals contribute to bonding. So I want you guys to pause, take a minute here, and try to figure out which of these orbitals contribute to bonding, both for the CH bonds and also for the CO bonds. All right. So hopefully you paused and it took a minute to identify these. Now let's go through this. So we'll start with the CH bonds. And essentially all we're trying to do is look for electron density between the CH bonds. And this here, so first the 1A1 and 2A1 are non-bonding orbitals. They have no density between any bonds. We'll move on to the 3A1, and there's not really a significant amount of electron density here between the hydrogen atoms. This is mostly density between the carbon and oxygen atoms. So this one is not bonding for the CH bonds. However, the 4A1 orbital is. We can see that there is electron density between the carbon and hydrogen atoms. So this is a bonding orbital for carbon and hydrogen bonds here. The 1B2 also has electron density between the carbon and hydrogen. So we have a bond there. This contributes to bonding. The 5A1 also contributes to bonding, and again, we see electron density between the carbons and hydrogens. And the 2B2 also does contribute to density. Again, we see density between carbon and hydrogen. Now, for carbon and oxygen, it's a different set of molecular orbitals. Some of them are the same and some are different. So the 3A1 contributes electron density between the carbon and oxygen. The 4A1 does not. We have a node. The 1B2 does. We see essentially a pi bond between carbon and oxygen here. The 5A1 also contributes. We have bonding density here between the orbitals. This is like 2pz orbitals here. And the 1B1 does as well, where the 2B1, again, we have a node. So the 3A1, 1B2, 5A1, and 1B1 contribute to the CO bond. And we could go through and do a similar thing to figure out, things like non-bonding. So the 3A1 and 1B1 are essentially non-bonding for carbon and hydrogen. And here we can have things like the 2B2 and the 4A1 are anti-bonding between carbon and oxygen. And we can go through and we can analyze these orbitals here. So these orbitals shown are just the ones that are occupied. If we wanted to figure that out, we would of course simply construct an MO diagram and then fill it in with the appropriate number of valence electrons, which in this case is 12. So 4 from the carbon, 6 from the oxygen, and then 2 from each hydrogen there. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then these are the core electrons. So these are all the filled MOs. There are more MOs that we can construct that correspond to unfilled orbitals, and then we start to see things like anti-bonding character between the carbon and hydrogens and so forth. Molecular orbital predictions like this give energy levels that are very comparable to experimental measurements of ionization energy. So if we were to ionize formaldehyde here, we'd have to pull an electron away from one of these MOs, and we can compare that energy it takes to do that to the energy we predict, and we get good numbers. And they also are pretty good at predicting the dipole moment. And of course, we can remember from last time that this dipole moment kind of idea, having a buildup of charge on the oxygen atom, is in good agreement with our localized bonding models. We expect, lone pairs maybe on oxygen, which would give us a buildup of charge, and we see that even when considering MO theory. If we want to, we can also consider the energy levels, and what we'll note is that, of course, these core electrons are very low in energy, whereas the rest of them are higher in energy, and we can see there's differences in spacing. Again, these are very complicated as to the reasons for these, and I won't expect you to do them. We can just calculate them using a program like Gaussian. Up to this point, we have not examined conjugated molecules. And I mentioned this earlier, but this is because localized models are totally insufficient to describe conjugated systems where the electrons are free to move throughout the system. To evaluate these systems, we are going to take a qualitative approach and use Huckel theory, which you may be familiar with from organic chemistry. So we'll start by considering the molecule butadiene and consider what the wave function of a conjugated molecular orbital for butadiene should be. All right, so this here might look scary, but it really isn't so bad. So if I ask you to think about what we're talking about for these delocalized models, you would say, well, if we have a conjugated pi system, that means we're merging together all of these p orbitals, and our electron can travel between the p orbitals. So what that means is simply that the wave function of this conjugated pi orbital is equal to some linear combination of p orbital from atom 1, 2, 3, and 4. In this case, we're choosing pz. Again, the designation there, what orbital you can choose is relatively arbitrary. So we have 4 p orbitals. We're adding them together to make a super conjugated pi orbital system, a delocalized model. Now, if we wanted to actually go and construct a wave function, what we would do is the exact same thing we did before for hydrogen. So we constructed wave functions for diatomic hydrogen. You remember it was pretty bad, and it's also going to be pretty bad here. So we're going to go through, we're going to skip a lot of the steps, but hopefully they're somewhat familiar to you. So we can end up with this horrible set of equations, and you'll hopefully recognize at least this part here as what we saw for doing this for the hydrogen molecule. And so this gives us a set of equations that we need to solve in order to figure out the constants, the contributions to our overall orbital from each of these atomic orbitals. And we get this set of 4 equations because we're putting in 4 orbitals. Now, to solve this, just like for the hydrogen atom, we need to go to a secular determinant. And so we get this big determinant. Now, it's not a simple 2x2 determinant, but it's a horrible 4x4 determinant. And we are not actually going to solve this, so don't be too scared about this. So this already is a pretty nasty looking problem. And so what we're going to do is make a lot of simplifying assumptions that are okay, but again, they're going to be very simplifying in order to make this something that we can more easily solve. And hopefully you recall that these capital H's and capital S's are shorthand for some nasty integrals. And in this case, the H11 is so if we have H11, H22, H33, so if we have any of the same number, that's simply the Coulomb integral. That's what we saw before. That's the total energy of these orbitals, right? And then if we have different ones, that is what's called the resonance integral. So for these H1, 2, 2, 1, 3, 1, 4, and other resonance integrals, talking about the interaction between one electron and a different atom. And then the S integrals here are the overlap integrals. And so the simplifying assumptions that we're going to make are as follows. We're going to assume that the overlap, if we're talking about the same orbital, is 1, and that's pretty good because, of course, your one atom completely overlaps with itself, so that's good. This one is a little bit less good. So this is saying the overlap of one atom and any other atom is 0. if that were true, we wouldn't have a bond. So this assumption is very, very simplifying and makes the math easier. We get a lot of good information out of it, but it's not true. Then we say that the HII integrals, so H11, 2, 2, 3, 3, 4, 4, are equal to alpha, where alpha is the negative ionization energy. So we're saying that it takes a certain amount of energy to pull an electron out of this p orbital, and that's what the energy of the p orbital is. Then we say that for the HII, or HIJ, I suppose, where j is plus or minus 1, so these off values here, we assign that a value of beta, which is just an adjustable parameter. And then for everything else, we set that to 0. So that simplifies this whole nasty matrix here into this one, which maybe still is nasty, but there's a lot of zeros, which makes a lot of cancellations possible. When you do this, this gives us a problem that we could then easily solve. This is something that you guys could probably not easily, but you guys could solve if I asked you to, and I won't. Solving this equation, as you'll do with the solutions, I'll give you the solutions to this equation and you'll solve that in the homework, gives 4 different answers that are the 4 energy levels that are possible. So this is a direct analogy to when we did this for the hydrogen atom and we mixed 2 orbitals, we mixed 2 1s orbitals and got 2 out, 1 bonding, 1 anti-bonding. Here we're mixing 4 p orbitals and we're getting 4 conjugated pi orbitals out. And this is the solution that we get. So you'll go over this in the homework, actually coming up with these values, but we get alpha plus 1.62 beta, alpha plus 0.62 beta, alpha minus 0.62 beta, and alpha minus 1.62 beta. And here beta, so alpha is a negative number and beta is also a negative number. So when we add alpha and beta together, we go down in energy, and we subtract beta from alpha, we go up in energy. And we get these 4 orbitals. And you can go back, plug these numbers in, and find that we don't actually have an even contribution of p orbitals. But what we do see is something that we expect, again, going all the way back to the particle in the box model. We see that this lowest energy orbital has only 1 node going through the bond or through the molecule here. And as we increase in energy, we get nodes going through the planes of the bond. So here we have 0 nodes through the bonds, 1 node, 2 node, 3 nodes, and we increase in nodes through the bonds here, just like we expect to do as we increase in energy. Another thing to note is that if we do this, and I will not make you do this, if you're interested, I can show you that I have done this in class to show that it's true. But as we increase the number of conjugated molecules, so say if we wanted to do this for hexatriene, we would then have 6 orbitals we mix together. And we can go through, do all of the same math. And what we'll note is that those 6 orbitals that we get are limited in the same space that these are. So no matter how many orbitals we try to do this with, we are limited in terms of the energy space that we can describe that goes from alpha plus 2 beta at the lowest extreme and alpha minus 2 beta at the highest extreme. So those are the limits that we get. And so what we get as we increase the size of the conjugated system is we have to cram more and more energy levels into a finite energy space. And what that gets us then is that the excitation from the HOMO to the LUMO gets smaller and smaller and smaller as we add more and more and more energy levels into this space. And what that means for us is that this transition, which will usually, this will take ultraviolet light to excite this transition. As I make this smaller and smaller and smaller, that transitions from ultraviolet to visible, and then I get colored molecules. And this is why our octatetraene molecule from lab 2 was yellow, because it started to absorb wavelengths around 400 nanometers, some visible purple light, so it reflected predominantly yellow light, and we observed it as yellow. This is true why any organic molecule would be colored, because it is absorbing visible light due to this phenomenon of having conjugated or aromatic systems. There are other ways to be colored. So inorganic pigments can be colored, again, due to electronic properties of inorganic atoms and molecules. And that's not what we're talking about here. We're talking about strictly organic molecules. So we can also apply this Huckel model to aromatic molecules. And there's actually a cute little strategy that we can use to do this. And essentially what this involves is taking the shape of our molecule. So this would be benzene here, a 6-membered aromatic molecule. And we circle the molecule and we set the center of the circle to be alpha, and the radius of this circle is 2 beta. So that means the lowest energy for this molecule is alpha plus 2 beta. The highest energy is alpha minus 2 beta. And then the other energy levels come when we hit the other vertices of our molecule here. So here we have 1 point at alpha minus 2 beta, 1 point at alpha plus 2 beta, and the rest of the energy levels should be situated at these peaks. And since we have a symmetric molecule, there are 2 energy levels at each of these points that have the same energy. What is the energy? We can calculate that simply by using geometry. So since the radius of the circle is 2 beta, we can make a triangle here. We have a 90-degree angle as we intersect this line. This angle here is 60 degrees. This comes from the angle of a perfect hexagram is 120 degrees. So if we cut that in half, which we have, we make a 60-degree angle. So that gives us an angle here of 30 degrees. The hypotenuse of this triangle is the radius of this circle, which is 2 beta. So that gives us the length here is alpha, and then plus 2 beta, the hypotenuse, times the sine of the angle. The sine of 30-degree angle is 1/2, so that gives us an alpha plus beta. And this would be alpha minus beta in the same way. And this gives us a cute little way to figure out the approximate energy levels for aromatic systems. We can then, of course, visualize this. And again, we see the same sorts of things that we saw for the last slide. So we have only one node cutting through the molecule here. And then as we increase in energy, we have one node going through in a couple of different ways. And we have 2 nodes, and we have 3 nodes for the highest energy orbitals. So using our simple Huckel model here, we get data that agrees pretty well with actual computational calculations or experimental measurements of the energies. We can also look at Huckel's rules, which will talk about what molecules are aromatic, would actually have what's called resonance stabilization. And these are essentially molecules that have 4n plus 2 electrons, where n is any integer. So if you have 4n plus 2 electrons, so say 6 electrons for benzene, you have 1, 2, 3, 4, 5, 6. You have all of these in bonding orbitals, and that gives you a stable aromatic molecule. That's also true for m equals 5. So this is simply coming from arguments using a pentagon instead of a hexagon. If you have 6 in that pentagon, you also have an aromatic molecule. So something like cyclopentene or something would actually be predicted to be more stable if it had an extra electron, if it was a radical, than if it was without. And for this reason, we often see 5-membered rings having nitrogen instead of carbon as one of their rings, which gives them that extra electron from the lone pair, gives them that extra resonance. If we have molecules with either 4n plus 1 or 4n plus 3, that's 1 too many. So thinking about benzene here, if we had either 5 or 7, we'd have 1, 2, 3, 4, 5, or 6, 7, we would have a radical, and that would not be very stable. And if we had only 4n, we would be in a diradical state, which would be very reactive, as is the case for cyclobutadiene here. So this figure over here is showing the resonance stabilization energy, or how stabilized these are compared to not being in aromatic forms. We can estimate this by simply taking a molecule that is in either linear or in a resonance, and talk about what's the difference between the energy if it's all in an aromatic molecule or not. And the difference there is the resonance stabilization energy. And we'll go over an example of this in class. And you can see that there are plenty of molecules that have resonance stabilization energy. There's also plenty that don't. So cyclobutadiene has 4n electrons, which would put it as a very reactive molecule, which means it's not stable. It has anti-aromaticity there. So that's all that I want to talk about here in this lecture. I'll conclude for the past 3 lectures on what we've been talking about. We've been comparing and contrasting valence bond theory, hybridization theory, which are localized bonding orbital, where molecular orbitals that we've talked about as well are delocalized models. So we have been comparing and contrasting localized bonding theories with delocalized bonding theories. What we found out last time is that despite this seeming contradiction of localized and delocalized orbitals, we could actually reconcile the two because they provide identical wave functions, so we can't distinguish them. Our valence bond theory helps us understand why molecules take the shapes that they do, but molecular orbital theory is more complete and can do things like actually describe bond angles, calculate energy levels, and so forth. And lastly, we use this Huckel model to describe qualitatively the energies for conjugated and aromatic molecules. And this can even be extended to solids, although I didn't quite cover that. We can talk about that in class if you're interested. So where we're going to go from here is we're going to now look at molecular electronic spectroscopy. Now that we've discussed why molecules are the way that they are, we can say, well, now that we know what the molecular orbitals would be, how do we transition between them and what kind of energy does that take and what does that look like? And that's where we'll be going in the next couple of lectures. So with that, I'll stop here and look forward to talking about this with you guys in class.